my first Lambda days, so I thought I'd start by introducing myself. So, hi, I'm Lisa, usually based in Berlin, where I do web dev things, also hobby game dev, recently turned artist, whatever that means. And in Berlin, I also help organize Clojure Bridge, which brings free programming workshops in Clojure to women and non-binary people. This is also how I got into Clojure a couple of years ago. And I also help organize crypto parties, which are informal gatherings where we teach people privacy-preserving and privacy-enhancing tools for their digital selves. So last year, about a year ago, I started learning Rust. I've since been happy enough to talk at 2 Rust conferences already. There are not that many, so this is kind of cool. And if you've been to Toby's talk previously, just before lunch, yes, I am the other person on the photo with him in the unicorn onesie. But enough about this, about me. Let's talk about Rust, the Rust programming language. And some key facts, or just a few introductory words. So Rust is a new systems programming language. It is aiming at the same realms that C and C++ aim at. Rust is furthermore safe, fast, and concurrent, all of these 3, which is kind of cool, and there's certain mechanisms in Rust that make this possible. It's also relatively young, so the first stable release, 0.1.10, only happened in 2015. Of course, there was some development prior to this, but there was highly influx, things were moving pretty much all over the place. There used to be a garbage collector which got thrown out, for example, and fun stuff. And I think the important part is that Rust is gaining popularity. The community is growing. It's a very friendly and welcoming community. So if you want to get into this, I think it's fairly easy, and you can see it with the ecosystem growing in different aspects. So some people focus on networking stuff, and other people find the crypto aspect really really interesting. And there's things for everyone, I think, and this is just the beginning. So I think in the next couple of years we will see more Rust in all sorts of areas. So this is Lambda days after all. So you might be thinking, oh, so Rust is actually a functional language? Is this why you're talking about it? And the answer is no, it's imperative, multi-paradigm things are going on, and you might be so what? This is every other language. Why would I care? And I want to give you 2 reasons. First of all, which is one of the things that I find important about functional programming is a paradigm that is, you can still apply a lot of functional thinking and techniques to even non-functional languages, and I think this is sort of the superpower with oh, I know how to solve this problem in a functional way, and then you hack your way around it. And this is one of the things that I really like doing if I learn a new language, and then just see is oh, what can I already bring from my background of other languages to the new language. And for example, this, one of these aspects can be functional programming. The other thing is that Rust, in its design, stemming from the fact that it is so young, it drew heavy inspiration from languages that came before it, and it also drew heavy inspiration from language design of functional programming languages. We will see a lot of things concepts that were directly inspired from Haskell, for example. And so I think there's a certain functional core that is inside of Rust. Also, I think it's just Rust is a really cool language, and I want to talk about it a lot. So I think it's also useful for people to just know a little bit about it, because I think Rust is here to stay, and yeah, as I already said, the future is Rusty. Okay, and I think I'm not the only person who is sort of this thinking of oh yeah, Rust, there's some functional aspects to it. This is a screenshot from the Humble Bundle website. So they offer bundles of digital things like games or ebooks for a certain amount of time, and you can pay what you want for it. And last week or 2 weeks ago, they launched a functional programming bundle. So you had 2 weeks to buy pay what you want for O'Reilly books on functional programming topics. And if you scrolled all the way down on the page, you saw the brand new programming Rust book that O'Reilly just launched in the same row as Clojure, Scala, and Haskell. I was okay, it's not just me. There's something about it. So yeah, before we actually start looking at Rust code though, I want to give a little disclaimer, because this is not, and it doesn't aim to be like a talk that should cover all aspects of Rust. I really want to like focus on things that I think are functional. There are certain other concepts that are also very important in Rust, but they don't fit in here. There's other talks that you can watch that cover those. The other thing is that, I do hope that after this talk you will start like maybe looking into Rust and like maybe like be a little open-minded about like, oh, maybe this is something for me. The thing is that the concepts in Rust are like very closely, like they work very closely together, and if you start learning it, it might not feel like a learning curve. It's like, oh, I know some things and then I learn more things. It's more like you hit a wall because all of the concepts hit you at once, and then you need to start figuring out how you can get through this wall. The cool thing is like once you have enough, or like you learned how to walk through this wall, you can walk through walls, and then there's nothing else in your way because you already know what to do. Okay, but let's get functional for real. I hope you're ready. As a little like guiding thing, I made a list so we can like check off a few things that I would like to talk about. I kept the list short so that it's not like too scary maybe. If it's like, oh my god, we're gonna sit here for hours and hours and just gonna like talk and talk and talk. It's like, no, it's hopefully it's short and sweet. Let's start with immutability. We like functional languages like immutable things because they prevent us from like mutating all over and then like totally messing up whatever state we wanted to have at some point. The cool thing is in Rust, when you define a variable, the default is immutable. So when you just like define a thing, you get an immutable thing, and that's nice. So here's some Rust. We have a main function, which is our entry to the program. We create a variable a with the let keyword, assign a string hello, and then if we try to reassign a to foo, the compiler tells us, no, cannot assign twice the immutable variable a. And this is like, oh, thank you, compiler. Of course, like I already assigned it here, I cannot mutate. The other thing is that you can opt into mutability though. So even though mutability is an option in Rust, I think the signal of saying, okay, the default is immutable and you can opt into mutability is kind of like the reverse of other like mainstream languages where mutability is the default and then you like have to opt into immutability if you want. So let's look how this works. With let mute a, we just indicate that like, okay, this variable can be mutable, and then if we were to reassign a with the string foo, a would hold foo. So yeah, this is possible. It's not super nice, but what to do. Aside from variables, there are also constants that you can use for if you really want to make sure that this value will never be touched, it will never be changed. And constants are always immutable. You use the const let word, the const keyword. It's then written, the name is written in all uppercase, and then you have to annotate type. So this is our first little type annotation in this example, and we say it's like after the call, like after the name of the constant, use colon, and then we say it's like this is going to be an unsigned 32-bit integer, and it's going to be 1000, because why not? And yeah, we will see different type annotations later in the examples, but I thought it's like I'm gonna like sneak it in really smoothly. On constants, type annotations are mandatory. On variables, they are optional, unless you do something really weird and the compiler gets confused, and then it would tell you, I'm very confused, please annotate type. There's also an example later. Okay, so we have this like, so if the default is immutable, so we just like work with the default and we like never opt into mutability. So it's like, we're fine. The thing is, Rust does not implement cool things like persistent data structures. So if you start dealing with like a lot of data and you like start like copying over, like generate like new things all the time, and then at one point Rust is like, okay, like allocate new stuff, no stuff, no stuff, and you will realize that this comes at a performance cost. So eventually you will just like see it's like, I guess I need to mutate now. womp womp. Luckily, there is Rust is a systems programming language, so you can implement your own your own persistent data structures. As for example, Bodil with IMRS did. This is a library where you can that you can pull into your project and just use the data structures that are defined there. They're always immutable. They're like persistent, and it's like nice. This is one way to do it. The other way, and this is the one point where I mention ownership and borrowing for the only time in this talk. Ownership and borrowing are big concepts in Rust of like how it manages to like guarantee type safety. And it's also like the guidelines and like the way the compiler holds your hand while you like deal with potentially mutable things is actually like, it's kind of like your safeguard. It's like, while this is technically a mutable thing, I will tell you exactly when you're allowed to like mutate it and when not. And this is kind of, this prevents a lot of like common errors or like common, yeah, rabbit holes or like your data falls into and you're like, what did I do? And yeah, Rust usually has your back with this. It's just a big topic that I will leave out for the rest of this talk. That was it for immutability. So we kind of have this like, okay, there are like some things where functional aspects shine through that we like, but like not really. But I guess let's look at functions, because functional programming without functions is kind of not functional programming. We already saw one function so far, which was the main function. So we have an fn keyword, the name of the function, parentheses, and in curly braces, the function body. In this case, we print hello world. So this is nice, but functions get cooler if we like add parameters to them. Functions can take parameters, unfortunately not an arbitrary number, so you like always have to define how many arguments a function can take in, so okay. But if we have params, we do have to annotate type, and this is where Rust is later than, like for example on variable assignment, is able to infer type, because we know from the function like what type we expect, and then from like the function as our central point of like type definition, we can then, or Rust can then like figure out what other types are needed. Okay, so let's like change the example a bit. I'm also now defining a function ID, which will take a param x of the unsigned 32-bit integer, and then in this function we will then print hello whatever we got as an argument, and then in main I call this ID function with 7. This would print hello 7. But we don't only like want to take things into a function, we would also like return things from a function. And if a function returns a value, you also want to like annotate type. Like you have to annotate type actually. So let's make the ID function like the actual ID function. So we take something in and we just like return the same thing, and both of them are of type of the unsigned 32-bit integer. And the return value is in the function signature indicated by this little arrow that then points to the type that we expect. And then in main we call hello, and then call ID 7. So cool. Question: what does the function return? This is something that I confused me a lot when I was like starting to look at like Rust code. It's like if I put the example back up, it's like okay, ID returns X, but like main doesn't return whatever like println evaluates to or something. There's no return statement, and it's like okay, so how does Rust know what the function returns? And this is indicated by this character, the semicolon, or the lack of the semicolon. And this is where Rust talks about statements, and like it's statements versus expressions sort of. So on one hand we have statements that perform actions but do not, they don't evaluate things, they don't like return something. Expressions on the other hand do exactly this. And expressions do not have a trailing semicolon. For whatever reason, somebody thought this makes sense. I don't know, but it's the way, and we have to deal with it. And no worries, you will get used to it. This has like certain other, like the statements and expressions thing has certain other implications. So Rust deals Rust treats function declarations as statements, but function calls as expressions. Okay. This, for example, means that statements cannot be assigned to variables, but expressions could be. And here comes a cliffhanger for functions, because you have to keep this in mind, because we will like later come back to this. Because functions is a big topic, I split it up into two, but there's something that kind of needs to go in the middle before we return to this. So, end of functions part 1. Let's talk about types and traits. As you've already seen, there are types in Rust. Rust is a statically typed language with type inference, so it can figure out things on its own. But what I actually want to talk about the type system is that Rust also has generic types and traits. What's a generic type? Generic types, or just generics, are stand-ins for concrete types that the compiler will later fill in for us. Traits are abstract implementations of functionality. You might know this from other languages as, for example, interfaces. They're not 100% the same, but very much the same. And traits, so like implementations of functionality, we can implement those on like concrete types. So we can like take a type that, for example, we defined, and then like put some more functionality that comes, for example, from a library, and do this. But we can also implement traits on generic types. So what exactly? Here's a little example, like just one line of code to like maybe illustrate this. So in this case, we have two traits, log and debug. And if I read this out loud, it says implement log for a generic type t, where t also implements debug. And then in the curly braces would come the actual implementation. But this is sort of like, okay, we implement the trait log for any generic, like for any type that is already like implementing debug. So it's like a trait constraint kind of like definition. So this is like, okay, this is kind of cool. We can work with this. And this like will be really cool if we look at another few concepts in Rust. I call the slide Enums and Pattern matching. Enums are another type in Rust with enumerated possible values. So we know exactly that a certain enum can be one of a set of like predefined set of options or variants. And these variants of an enum can also hold generic types. What? This is like, it's all very abstract, I know. But bear with me. I have an example. This is an enum that Rust comes with. It's called the option enum. And option of a generic type t can either be some of t or none. And if you're thinking like, oh, I think I've seen this before, you probably have. Here's a little example function that is called +1. It will take an option of an integer, and it will also return the option of an integer. And then in the function body, we match on the parameter that we get. So like we get an option, and then we match on it, and then we can decide. So if we know that option can only be one of two things, some of something or none. So if it's none, do nothing, like return none. But if it's some, we can access the value in sum, and then like return sum of whatever was in there +1. This is why the function is called +1. And this is pretty cool. If I then were to call this function +1, and then we give it a sum of 5, and then we call unwrap. Because enums are lazy evaluated, so if I like would not use the unwrap and just like say +1 and sum, this would just sit there and be there and just like wait for it to be like accessed. And like, for example, we can call unwrap to like then access whatever value we have. Then yeah, we can see what like is actually in there. Rust people actually don't like unwrap that much. I used it because we all know that monads are like burritos and you need to like unwrap them. And like a nicer way would, for example, be calling expect and then like have the option to pass in a string for if there's something that like unexpectedly happens, like we have like some sort of error message that we can use for debugging, for example. And yeah, this is just like a little tiny example of cool things with like types and also pattern matching that Rust makes heavy use of. So like we have certain error types that you can like match on error types, and then handle errors differently depending on what kinds of situations you find yourself in. And this is really cool. Nice. So we think that like types are cool, and like with pattern matching and stuff, we can like really like do some like cool things that like, I don't know, like maybe like Haskell people do sometimes, but we still have like kind of like a thing that we didn't talk about with functions. So I think it's time for functions part 2, higher order functions. So higher order functions are functions that take other functions as input and like also return other functions, or like taking functions in and returning functions. In Rust we have a little bit of a problem with this. So if we define a function in Rust, the name that we give that function will become part of the function type. So what does that mean? This means that if I define 2 functions with the exact same function signature, the types of these 2 functions would be different. This in turn means, and since we like need to always annotate the type of whatever input or output we have of a function, is that we basically can't dynamically create functions and like pass them around as we would usually do. I put here like easily in brackets because there is a way if you like want to deal with function pointers, but it's probably not very economic to like go that way. So like this is kind of like a bummer. It's like, okay, this is kind of like really raining on my functional parade. The other thing is that like functions also are not able to like capture values from their environment. They're just like, if I were to like, if I could, or like in our example, like create a function dynamically and then pass it around, certain things that like, you know, capturing like environment and then like things like, okay, we can use this from wherever we define this function and like then pass it on. This doesn't work because functions are just like, I don't care what's around me. I just don't care what, like, I only care about what's inside of me. So of course this would be not like a functional talk if I were to stop here and say it's like, oh yeah, you can't actually do any of these things with higher order functions in Rust. Rust has another way of working around this, because Rust wants you to do functional things in it. And the thing that Rust has is closures. Closures in Rust are anonymous functions that do have the ability to like capture values from their environment. Closures can be saved as variables and used and returned from other functions. This is the reason why closures are implemented into Rust. This is like what people like. Rust people think like, we really want this because this is really cool and useful. We should put this into our language. So let's define a closure. We basically assign a variable, let a closure, for example, and after the equals we use 2 pipes, which is also quite nice. The pipe character is in Rust only appears in the context of a closure. So if you see pipes, it's a closure. So in pipes we put in the param, the argument, and then in the curly braces like the body of the closure. In this case I just multiply our parameter by itself and return that, and then I could call it like just like this. And you might have noticed that for closures there are no type annotations necessary. They are optional, you can if you want, but it's not necessary. And the reason for this is that the assumption is that if you, for example, write a library, we would probably expose a function or like some sort of like function interface to like people so that other developers could then use your function. And then Rust needs to check, okay, are these inputs what I want them to be? Otherwise I'm just gonna like yell at you that this is not possible. The other thing is that you would probably not expose a closure, you would like generate it and like use it internally. So it's kind of like, okay, we don't make this mandatory here. In case you do want to like annotate type, you can, but usually Rust is able to like figure out from like the first run of the program to say, okay, these are the types we can expect. I also put a link here where there's like a description of like how to like also implement memoization with closures and like custom types, but this is an example that I will not run through in this talk, but it's really cool. Okay, So now we have closures, so like anonymous functions, but we still don't have like, I still really haven't talked about higher order functions. Whereas our like map and fold or reduce and like all these things. And in Rust, they come in the form of iterators. Iterators are a trait, so abstract functionality, and that we can also implement on our own types. And the iterator is sort of like defined as functionality that handles the iteration on a sequence for you. Also, like other gotchas, iterators are thread safe. Also, iterators are lazy. Nice. Let's create an iterator from a sequence. In this case, I'll create a vector v1, and just like in the vector, I put the numbers 1 to 5. And then I create a second variable, v2, that would hold our iterator. And this is just, I create this iterator by calling iter on our sequence. Okay, now we have an iterator. What do? We can make a for loop. Yay! No, nobody likes for loops. It's a possibility, but this is where iterators really shine. Iterators can take closures as arguments, and usually we deal with two types of iterators. There's the consuming kind, where you actually like kick off the evaluation of an iterator and like progress the sequence, and then do whatever needs to be done, what you define. So I have an example where we call fold on our iterator. In this example, I only have like a vector of 1 to 4. We call iter on the sequence, get the iterator, and then we call fold. Fold takes as first value, as first parameter, the starting value of the accumulator, and then we have pipes, so it's a closure. We have this, then it takes the accumulator and then a reference to x, don't mind the reference, so we get each element in the sequence. And then as function body, which I put on one line here, and you can omit the curly braces, we just like add x to our accumulator. And then v2 would not hold the iterator, but the sum of like the numbers in the sequence, so in this case 10, if I'm not mistaken, because we just basically added all the numbers. We can not only consume iterators, we can also adapt them, so like transform them from one kind of iterator into another one. And this is also really cool. Here's an example where we use map as a iterator as an adapter. So in this case, after the vector, after I create the iterator, I call map, and then I give it a closure which adds 1 to each element in the sequence. If I were to stop here, v2 would only hold an iterator that is not yet evaluated. It would just sit there and wait for me to like do something with it. In this case though, after map, I then call fold with the same closure. Though after we added 1 to each value in the vector, we then sum up everything else. And yeah, this is it. And there's all kinds of methods that can be used with iterators. So there's like all your standard filter, zip, and like whatever you want to do with it. I think we have a little bit of time, and as I said, traits can be implemented on your own types, and also the iterator type can be implemented on your own types. So I thought, let's look at a bit of an example. This example I took from the Rust programming language book, which is available online for free. And in this example, we will create our own type, which will be a counter that holds a property count that we then will count up. The thing in this example is that we will only count up to 5, and then we will stop. So how do I do this in Rust? I call struct. With the struct keyword, I say it's like, oh, I want to have a new type. You call it counter. It holds the property count with the unsigned 32-bit integer, for example. Then we implement this counter by defining like what should be done if we create a new counter. So this new function will return the counter type, and the count property of this new counter will be set to 0. Now the important part, the implementation of the iterator. So we implement iterator for counter. Then we have to define the type, which is an associated type. So what each element in the sequence like what type this will be. In our case, an unsigned 32-bit integer. And then we define next. And next is the only function that we need to implement to like have access to like all the other possibilities of the iterator universe, basically. And next is a function that defines like what should I do when I jump from one element in the sequence to the next. And then we see that that next takes like a mutable reference to itself, so we call it on the counter object, if you will. And then we return an option that holds the associated type that we define. So like an option of, in this case, the unsigned 32-bit integer. The actual, like, if we want to count from 0 to 5, what do? We just like count up by 1. This is what like this function does. So it's like self count plus 1 plus equals 1. And then since we only want to like count up to 5 and don't care about the rest, so if we like still until we have reached 6, we return sum of whatever we have as like our internal counter, and if we reach 6, we return none, and this tells the iterator that we will stop. Okay, let's use this. In our main function, we can like we can create a new counter by and assign it to a variable by calling counter : new, which is like a little constructor. And then what in this case I want to do is like, okay, we count up to 5, but then I only want to have the even numbers from our little counter. So I create a variable even nums, which will be of type vector, like it will be a vector of unsigned 32-bit integers. This is something where the Rust compiler told me, I don't know what you're doing, please tell me what type even nums will have. And I was like, okay, I can tell you. And then we say, it's like, okay, from our counter, which is now directly implementing the iterator. So before we needed to call .iter on a sequence to return an iterator, but now counter itself is an iterator. So we can call filter directly on counter, which takes a closure, which is like checking like modulo 2 is like, is it 0 or not? So it's like, is it even or odd? And then return either true or false. And then, since filter is also just a adapter, this would not kick off evaluation yet. So we need to call a consuming thing. In this case, I chose collect, which just like puts every value that it like receives into a vector, and this is where the vector type comes from. If I then want to print like even numbers or like even, and then the whatever I got back, I would get this 2 and 4, which is when we count to 5, give me all the even things, 2 and 4. It's not that hard, is it? No. Okay, that was the checklist. I kind of cheated by like always segueing in each topic into like different directions a bit, but I hope you got a little bit of an overview of like some of the concepts in Rust. And it's time to take a breather. Cool. This is almost all. I don't think that I told you a lot of new things or like stunning, impressive things that are new in like the world of computing. No, it's just that, and this is kind of like the point where Rust, even though it's like systems level, it's not scary. This is all like things that you know from other languages that you can use right now. And I think there's also like the parts of Rust that were influenced by Haskell and OCaml. I think you can see this in the type system, and the if you look around the Rust ecosystem, there's like heavy use of higher order functions in the way that I've shown you, or the pattern matching. And this is which leads me to like my kind of like call to action that Rust is new and it still like needs to be explored. And I would really like to have more people like look into the functional aspects, because I feel a lot of times people talk about exactly like ownership and borrowing and like all these things that like they are important, but there's so much cooler stuff that is just waiting for us to like get into this and like talk about it and like help other people jump onto this wagon that is yeah, gonna be the future, I think. I want to give a shout out to a couple of people in Berlin, Florian and Andrew, who helped me review earlier versions of this talk, and also to Carol, who did a lot of like rewriting of the Rust programming language book, which makes it so much better and so much easier to understand. I really recommend it if you want to start somewhere. Start by reading this book. And this is it. Thank you for your attention.
Can you Can you tell us a bit about where it's headed? Do you have any idea, sort of, if Rust is moving in the direction of implementing more functional concepts, or what's the talk in the community?
That's a good question. So the Rust community is right now composed of like people coming from all kinds of backgrounds. Like there are some C people, but there's also like Ruby, Python, JavaScript people. They come from everywhere, and there's still like a lot of, the community is growing right now, and there's no like specific direction, and it's very much led by what people want to do right now. I was asked like yesterday about, oh, Rust for embedded systems, and I'm like, yeah, totally, but I don't know any people who do this right now, and like I think if there's a couple of people who like things like, oh, we should like totally push forward in that direction, like Rust would go there. And I think it's the same with functional Rust. So if like more people would like come and say like, these features are already really cool, I want more of this, there's definitely like the chance that like Rust can evolve in this direction. And this is like the cool thing, that it's such a new like language. There's like input from the community is highly appreciated, and then yeah, if you want this, you can do it. And this is also like kind of like why I gave this talk, because I want more people to like do this. Yeah, I hope this answers the question.
Hi.
Hi.
So when you said that the names of functions are part of their type, that caught me as a really weird thing. Do you have any insight into why that is? Or is there a good reason for doing
That's a good question.
that way?
It's a very good question, because I was also surprised by this. I'm not 100% sure, but I kind of assume that's also part of the Rust 1 safety, and we need to check a lot of things to like have this kind of safety. I didn't talk about like how Rust deals with like memory management or anything, but this like part of this. We want safety, and like safety is the first concern, which is why we have a lot of these constraints. And I'm pretty sure that for a reason that I don't fully understand, making function names part of the type of a function is part of this. We need to check this, so we like want to have this. If anybody else has like knows the exact reason, please say. But I think it has definitely to do with this. So.
Did we have a question down here?
Ah.
Okay. So any more questions? Cool.
Are there any automatic conversions from function to closure, or you have to write like x, f of x, instead of just passing f to map?
As far as I know, there are no automatic anything that like does this automatically. So you have to like do it manually, basically.
As I understand, this is a systems language, so the performance consideration going to be a pretty huge thing, right? So is there any performance penalty for using higher abstraction? If your whole system going to build on your functions and maps and reduces, and in the whole heart it is imperative language, is the performance going to be still considerable to C++ version?
Excellent question. This was of course also like part of the things that like Rust people wanted to like. We want to have this like possibility of like do higher level like programming, even though it's a systems level language, and Rust calls them zero cost abstractions. So like we can have nice things like MapReduce and like all this kinds of stuff, and they run at basically the exact like just exactly as fast as it would if you would like to construct your own like little for loops. So this is like once Rust compiles your code, it will basically do this, but it will do this for you. So like you can like write your programs in a very like high-level looking style, and then the compiler will do like all the work to make sure that this is like gets written down to like a bare bones thing, and it will like be just as fast. And this is really cool. So like there's no performance drawbacks for using this in Rust, which is really cool.